I welcome all of you to the 83rd lecture in the lecture series in nonlinear dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce today's speaker, Professor Amit Apte from Indian Institute of Science Education and Research, popularly known as ISER, Pune. Professor Amit Apte obtained his PhD from University of Texas at Austin in the year 2004. He carried out his postdoctoral studies at Statistical and Applied Mathematical Sciences Institute, UNC Chapel Hill, and Mathematical Sciences Research Institute, MSRI, Berkeley. He then came back to India and joined as a faculty in TAFR Center for Applicable Mathematics, Bengaluru in the year 2007. He then moved to ICTS, Bangalore in the year 2013. In 2021, he joined as a faculty in ISER, Pune, and right now he is working as a professor in the Department of Data Science, which they are creating now. Professor Amit Apte research interest covers data assimilation, monsoon modeling, particle and column filtering, dynamical systems, Hamiltonian systems, renormalization group, and transition to chaos. He is serving as an editorial board member in nonlinear process in geophysics. He has presented a large number of popular talks and published notable research articles in his area of expertise. He has guided more than 10 students for their PhD. Professor Amit has large number of collaborators both in India and abroad. With this short introduction, now I invite Professor Amit Apte to deliver his lecture. Over to you, Professor. You are muted. Yeah.
Sorry, I just realized that I had.
Yeah.
Okay. Yeah. Can you see the screen?
Yes.
Yes. Okay.
Yeah.
Thanks a lot, Professor Santilvelan, for this nice introduction and for the invitation to speak here. And so I guess I will start with a introduction to the topic, very general introduction, and then I will get to talking specifically about the stability and asymptotic behavior of the systems we are considering. So if I don't get to the very end of it, I think that's okay. But if you have questions, you can feel free to stop me and ask me in the middle. I will try to monitor the chat. If I don't, then if there are questions, then I'm happy to take the questions in the middle as well. So if you want to ask the questions in the middle, that's okay with me. Okay, so with that, let's get started. Yeah, so okay. Sorry, I joined from my phone, but just to see if I can monitor the chat, but I forgot to put it on mute. Apologies for that. Let me do that right now. And yeah, okay. So I guess why these pictures? Well, I'm not sure if they are fake or not. Who knows? But part of the reason is as follows. Suppose you are standing somewhere on the seashore here, where the birds are, or standing on some rock here, and you want to try to understand whether the wave that's coming towards you will reach you or not. What type of question, what type of modeling, and what type of mathematical techniques can help you answer that question? That's kind of what I would like to convey. Right? This is, so to say, the crux of the filtering problem, or what is called data assimilation in earth sciences. And hopefully, at least halfway through the talk, you would be convinced that the mathematical framework I'll be talking about at least tries to answer these questions. And let's see if part of the after the introduction you're not convinced of it, please ask me, and we can come back to this picture later. Okay, so briefly, as I said, I will start with the introduction to the topic. I'll specifically talk about a couple of algorithms, particle and Kalman filters that are used in order to answer these questions that I just asked. And then I will go towards understanding what do you mean by stability of such systems and some of the algorithms for assessing the numerical stability of these, and I'll finish with some open questions. So most of this will be based on the works that are here, and I guess I'll be happy to share the slides, so these will be available to you later. Okay, so what exactly is data assimilation? The main context of the problem was basically from earth sciences, and in particular, think of the problem of predicting a weather. If you want to predict the weather, what's the system that you want to talk about? It's the coupled ocean atmosphere dynamical system. And in fact, it's these days not just the ocean and atmosphere, but many of the systems used in practice also have a component which is the land and the sea ice and so on and so forth. So it has become significantly more complicated as the computing power has become larger. But let's just stick to saying that the atmosphere or the ocean is a dynamical system. That is what we want to study. And the kind of model that we have for this system is basically a discretization of the partial differential equations that describe this. So it is a deterministic high dimensional model, and in particular, it's also chaotic. In this case, high dimensional means that it could be anywhere between 10 to 100 million or even a billion dimensions nowadays. Typically available at some implementation, numerical implementation, containing several thousands of lines of hundreds of thousands of lines of code. And that's a system that we want to study using the observational data, which is time dependent. For example, satellite observations over the last 20 years or 30 years. And these are very sparse compared to the dimension of the system. So the number of satellite observations is growing essentially exponentially. I'll come to that later. But even then, it is still very sparse observations compared to the dimension of the system. So combining these aspects of the system, the dynamical model and observed data, we want to estimate the state, and in particular, the state of, say, the ocean atmosphere system and the associated uncertainty in our estimates. So naturally, in a Bayesian framework, we need to identify what is the prior knowledge that we have about the system and what is the observational likelihood for this. And in this setting, the prior basically comes from the model simulations, because the dynamical model, which is the numerical implementation that we have, we can run it multiple times. We can create a probability distribution out of it, but that is just understanding the model behavior, and hence that is the prior knowledge that we have. Once we get the observational data and the associated uncertainty, then that gives us a likelihood. The observational probabilities, that's the likelihood. And combining the two in the Bayesian framework, the exact details of which will follow in the next 20 minutes or so, we get the posterior in terms of typically a sample, and that ensemble of state estimates gives us the state estimate as well as the associated uncertainty. And that's the object of study in this talk. Yeah? In particular, for example, such a sample, the Bayesian sample obtained by this process, for example, for the last 30 to 50 years, is what is called reanalysis. And the reanalysis essentially provides the best guess that we have to understand the past climate of the Earth. And this is used quite widely in climate studies, even trying to understand how the models are behaving, what the lacunae are, and so on and so forth. Yeah? Okay. So this is a kind of a picture that we'll keep coming back to. We have a actual state of the system, the red, this solid trajectory that I'm showing, indicating the dynamics of a true state that we want to try to observe. Think of this as the trajectory of the atmosphere. We don't have the direct observation of all of this. We can only observe it discretely in time and also very sparsely. So these are kind of the blue dots. The blue dots are the sparse observations of the system that we have. We do not have the red full trajectory. And using these blue dots and the model that we have, we want to make predictions. So if you have a model, and if we start with a bunch of initial conditions for the model, we can get a state estimate. We can run the model, go forward in time, and these could be these green trajectories that I'm showing here. But as you can imagine, with a chaotic system, these will deviate away from the actual dynamics of the system. We want to find a method by which to make corrections such that our corrected system is now again close to the true system that we want to observe, in this case, the atmosphere. Again, if we go forward in time, because of chaos, there will be divergence. And again, we want to do the correction again, and so on and so forth. So this is a repeated process in time. That is what is called data assimilation. Basically, how to incorporate the frequent observations of the system into the model in order to let the system be close to the actual trajectory of the system. Right? So this process of combining the dynamics and observations to get the posterior distribution is called data assimilation. So we'll come to another definition, similar, more precise definition later. Because of the chaotic nature, we absolutely have to incorporate probabilistic description and
Amit,
yes,
can I stop you, please?
Sure,
of course. Yes,
please.
Previous slide.
Yeah,
Sure.
Sure.
You said if frequent observations. I mean, how frequent? That should be a step size, right? Time step.
Yes, we will come to that.
Okay.
At some point, I will maybe mention about the relation between the frequency of observations and things like Lyapunov exponents and so on at a later stage. But broadly, if the frequency of if the time step between observation is of the order of the largest 1 over the largest Lyapunov exponent, the Lyapunov time scale, or larger than that, this process is not as efficient as you can imagine. And the frequent observation means that they should be sufficiently more frequent than the Lyapunov time scale.
Nice.
That's broadly the rule of thumb that's used.
Thank you.
Yeah. Okay. So other question? There is some other question, I think.
I had a basic question here see when you have this Bayesian setup.
Yeah.
So you're putting a prior on this initial state, is that correct?
Yes, that's true. Yeah. Mm-hmm.
And that is the thing that you want to infer in the end.
Well, I guess if it depends on the context, what you want, what you're interested in. For example, if you're thinking of weather prediction problems, then what you are interested in is, let's say this is the last time of observation today, say, then you are really interested in the future, next 3, 4 days, 5 days, 10 days. If you are studying the past climate, let's say a climate over the last 50 years, then it is the probability distribution in the past that is of interest. So it depends on the problem of interest that decides what is it that you really want to infer from this. It's not always necessarily the initial condition per se. Does that answer your question?
Yeah, I guess I was. So I mean, I just had a more broader question then.
Yeah.
So in this case, you say all these are deterministic systems.
Yeah.
And so, to put it in this Bayesian context, you need to introduce likelihoods and so on. So the likelihoods come from this prior on the initial state. Is that where the likelihoods are coming from?
No, the likelihoods are basically the observational log. The observational uncertainty gives us the likelihood. The prior coming from the model outputs is the prior. So combining the product of the prior. So I guess one possibility is that once we come to the mathematical framework, maybe things will become slightly more precise and you can ask the question, or if you,
Thank you. That sounds good. And I think that helps.
Okay, fine. So let's wait for another maybe 10 minutes or so, and then we can come back to this. Okay, so why do we need probabilistic description if we are dealing with deterministic systems in the first place? Well, one simple thing is that observations always come with uncertainties, and to describe uncertainties, you need probabilities. That's a naive answer. But in particular, for chaotic systems, why do we need probability is I guess explained in this trajectory. So one characteristic of these kind of chaotic systems with attractors is that almost every trajectory looks the same and has the same statistic. That's basically kind of the behavior of the ergodicity of the system, right? So if you try to look at trajectories, they will be on the attractor, and hence their statistical behavior will be similar to each other. Well, that's not quite of interest, because what we're interested in is the specific trajectory that is the atmosphere or the ocean. And that has the additional complication that the trajectories which are starting nearby diverge away from each other exponentially. This is the result of the positive level of exponents of the system, and that's part of the hallmark of the chaos. So essentially, chaotic systems have both of these aspects combined into one. Right? They may sound contradictory, but they're not at all. Because the first one is statistical behavior, the second one is the description of specific trajectories themselves. So the consequence, in a way, is that for deterministic predictions beyond of the order of 1 over the Lyapunov time scale, or beyond the Lyapunov time scale, are impossible in the sense that the errors in such, or uncertainties in such predictions, become quite large. So that's one consequence. And hence, what we want to really do is to make predictions in terms of the probability and uncertainty with it. Right? And so these probabilistic predictions require frequent observations, as we described a little bit earlier. How frequent? Well, they have to be something smaller than the order of the Lyapunov time scale, in order for the uncertainty to be smaller than the long-term statistics of the system. Right? Otherwise, we are not really capturing anything. So just as an aside, even for the solar system, these uncertainties can grow, and if you want to think of the solar system of the order of several hundreds of millions of years, then it is in fact impossible to do this kind of deterministic predictions, and you need to resort to probabilistic predictions for the solar system as well. Okay, so that's an aside, but so this is what requires us to have observations, right? And what kind of observations do we actually have for the atmospheric oceanic system these days? And that has grown tremendously over the last 2 or 3 decades or so. And the observational data sets are essentially increasing kind of exponentially in size these days. So probably the exponential increase will not sustain for too long, but anyway. And so here are a few, so to say, this is one of the reviews which describes this, as well as some of the data sets that are available and where they come from and so on and so forth. So I will not talk about the details. Largely, they come from satellites nowadays, and not as much from ground-based observations or ships and so on and so forth. Yeah. So studying these observations, how to obtain them, and so on and so forth. For example, what do the satellite observations actually tell you about the ocean or the atmosphere? That's a interesting problem in itself, but we will not discuss this. We'll simply take these observations on the face value as given to us by the atmospheric scientist. And in addition to the observational data, there is also a large amount of simulational data sets coming from simulation available to us. So as the computing facilities have grown, the simulation data sets have grown in size. And these are essentially limited by the kind of computing and storage one is willing to utilize. It's of course also limited by the fidelity of these models. If the models are not good enough, then we will have large amount of data sets, but that may not be relevant, but that depends on how good of a model you have. And in particular, it also depends on these data assimilation methodologies that I will talk about. So such again, some of the references of what kind of data sets are available and so on are here, but I will not dwell on the details right now. Yeah? So just a quick comment, these kind of data sets, combining the observations and simulations, is what is really used to make inferences about the past and then hence also project into the future, that are used in reports such as the IPCC report on climate change and so on and so forth. Yeah? So these are really crucial and important questions going forward in time. So starting with some more mathematical and precise description of this problem, what we have in hand is something like a dynamical model that can be written. For now, I'll just talk about discrete time formulation. So you have a description going from time t-1 to time t, and this could be either described as a Markov transition kernel in terms of probabilistic formulation, or it could simply be a deterministic mapping from time t-1 to time t. We will mostly stick to the deterministic case here, but in general setup, it could be a probabilistic forward map. Okay, what we have are the observations, as I said, and the most common assumption, which is what leads to filtering theory, is that the observation at time t, yt, is a function of the state of the system at time t, plus possibly some noise. Additivity of noise is not necessary as an assumption, but that's what we'll deal with currently. If you have multiplicative noise, things become technically quite more challenging, and at this stage, it's not quite necessary to introduce that. So that's one of the main assumptions. And given this model that we assume to be the dynamical model available and the set of observations that we have, what we want to do is to estimate the state of the system at any given time t, given a set of observations. So suppose the observations are given from time 0 to time tn over this time period, then there are three broad classes of problems. You may want to estimate the state of the system at the final time, that is the time of the final observation. That's called a filtering problem. Estimating the state at any time before that is called smoothing. In some sense, you're trying to smooth the trajectory of the system. And estimating the state beyond this time is the prediction problem. For example, weather prediction or climate prediction kind of problems. Yeah. In the probabilistic language, this gets transferred to the following. Suppose we have the observations from time 0, or in this case, time 1 to time t, and those are concatenated to write as y1 through t. So all these observations, given all the observations y1 to t, conditioned on these observations, we want to find a probability distribution, the state at time t, xt. And in this case, I'm stating this as essentially a filtering theory problem, right? So the basic filtering theory problem is estimating the state at time t when we have observations from time 1 to time t. And that is indicated in this case by yt. Yeah, so it is the probability density or probability distribution that we want to estimate instead of trying to estimate just the state of the system xt at time t. The deterministic formulation will be kind of like an inverse problem. Given the observations y1 through t, find a function that maps the observation to the state at time t. So you want to write xt as a function of these observations, and that can be thought of as an inverse problem formulation, but we'll not discuss that. And there is a similar prediction and smoothing problem, but I will not be talking about smoothing and prediction, so I'll skip that for now. So is there a question about this? Hopefully this answers the question about what is the prior and what is the posterior in a sense. In this case, or maybe one more slide later, the prior will become explicit. Right now, I'm just stating the posterior here. And the likelihood is the distribution of the observations. Other question? There is one more question. Yeah.
Yes.
Yeah.
Please go ahead.
Yeah, can I guess I wanted to ask what happens if the kernel is deterministic. I mean, if your dynamical model is deterministic, so then...
So the mathematical framework remains... So let me state a possible answer to this. So the mathematical formulation doesn't change at all. It's still exactly the same formulation. We want to understand the posterior distribution given these objects, right? And in this case, effectively, you can think of this as a delta distribution. PM will be delta of xt minus m xt minus 1. And it's a singular limit that can be dealt with appropriately, but the formulation remains the same.
Okay, thank you.
Okay, I will skip this continuous time formulation because I'll not really talk much about the continuous time setup. We can skip this continuous time part for now. And just to note that, okay, well, the reason for putting the continuous time, because there are some results that I will talk about at the end. But if I have time, maybe I will skip that part completely. So the continuous time formulation has a parallel to the discrete time formulation I set up, and that's pretty much all I have to say right now. Okay, so coming back to what I started with, just to relate to what I started with this breaking of waves, think of data assimilation problem as trying to estimate which wave will reach you while you're standing on the seashore. If that sounds trivial, well, that's not quite the case, because, for example, think of this as you have a house on the seashore and you want to find insurance for it for the next 50 years, and then this problem becomes extremely important, right? Okay, anyway, similarly, for example, what are the minimum and maximum temperatures in various cities in India for the next 20 days, tomorrow, or over the next month, and so on. Yeah. On much longer time scale, this could be a problem of design. What will be the average temperature month by month up to 2050? And then how do you design certain aspects of the city in order to deal with possible changes in the temperature, so on and so forth. Okay, so these are some of the applications. Some of the mathematical or physical characteristics are that, as we discussed, these models are coming from either Navier-Stokes equation or some appropriate physical model. So there are good physical theories that describe these systems, but the models based on these theories may not be as good. And at some point, if you have questions, we can discuss the distinction between theories and models, but let's not get into that philosophical discussion right now. And but we know that these kind of weather models do not describe the system completely. There are missing bits and pieces, and that's what we need to deal with. The systems are nonlinear, chaotic. They are multi-scale. There are multiple temporal and spatial scales involved in this system. And observation that we have are noisy, they're partial, as I said earlier, and they're discrete in time. And so combining all these characteristics, we want to solve the problem of state estimation or prediction. And so coming back to the picture which I had put up earlier, now one possible kind of definition of data assimilation problem is it's a black art of optimally incorporating this partial and noisy observational data of a system, which itself is chaotic, nonlinear, complex, and high-dimensional system, for which what we have is an imperfect model. And imperfect, the model of the dynamics of the system and the observational data are both imperfect. And we want to combine all of these aspects in order to get the estimate and the associated uncertainty. That's one definition of the data assimilation problem. The main applications are, as I said earlier, weather and climate studies. But nowadays, more and more, as better models and better data sets are available, they are used in biological system, industrial applications, and so on and so forth. But the main challenges, both from the mathematical and computational side, are that these systems are complex, multi-scale systems. There are significant uncertainties in modeling these processes. And then there are associated computational challenges. These become very large dynamical systems, and just simulating them becomes a computational challenge. Yeah, so, okay. I had to add this, right? I'm supposed to be in the Department of Data Science nowadays. So one way to think about this is, how do you do data science if you have chaotic dynamical systems? So, okay. Any questions up to this stage? I guess this was sort of the basic introduction to data assimilation, and now we'll get to talk about specific algorithms and their stability in the next half an hour or so. Questions? No. Okay, so so the actual, how do we deal with this mathematical formulation? essentially it is a Monte Carlo approximation that gives rise to the practically applicable filters for this system. So here is a one-line description of what these algorithms do. Suppose we have, since we have a dynamical system, we want to have a dynamical evaluation of this algorithms, of this posterior, right? So suppose we have the posterior distribution at time t minus 1, which is the probability distribution of the state at time t minus 1, conditioned on observations up to time t minus 1. And we want to use this and other knowledge of the system to get the same posterior, but now at time t. So the distribution for state at time t, given the observations up to the time t. And there's a natural two-step process, and this is why the discrete time description helps in describing it conceptually, that if we have the state at time t minus 1, we know how to go forward to time t, and that is what is the forecasting or the prediction model that we have. And given the state at time t, but now incorporating observations at time t, we would use the update or the analysis, which will be the Bayesian state, to get the posterior at time t. So it will be a two-step process. So as I said in words earlier, the prediction going from, or the forecast going from time t minus 1 to time t will use the dynamical model. And explicitly, it is written down in the following form. You have the probability at time t minus 1, and you use the Markov transition density to get to time t. Yeah. And notice that in all of this equation, the observations are only up to time t minus 1 here, and only up to time t minus 1 here as well. So we have not yet used the observation at time t. Once we have this forecast or the prediction, then we can use a Bayes rule using the likelihood of the observations in order to get the update at time t. So this was the forecast, simply the product of the forecast, which now acts as a prior at time t, and the likelihood at time t. The product of the two gives the posterior at time t. So the prior at time t and the posterior and the likelihood multiplied together, right? And so that's the simplest mathematical description that we can think about. And combining the two, essentially that gives a recursion relation that can be written in the following form over here. Yeah. Okay, so that's not a very useful algorithm because, for example, or description. For example, remember I said that the system is, let's say, a million dimensions or 10 million dimensions. And this integral is a 10 million dimensional integral. So essentially impossible to do. There is no way you can do this at all. What we can do is do something like a Monte Carlo approximation of these objects. And that's what I will talk about in the next slide. So the Monte Carlo, I guess this is a picture. Let's skip this for now. And the Monte Carlo approximation of this recursion relation looks like this. So what we have, I will of course be writing everything in terms of now sample. So, and these will be usually important samples or weighted samples. So there will be a sample associated with the weight for each sample point. And this will be either for this analysis or the prediction that I talked about in the earlier slide, right? And for the prediction, you have the prediction will be indicated by the superscript F and analysis by A. So the two-step process will simply be, in the case of, let's say, the Kalman filter, you have a forecast to go from, or you have a description at time, the forecast at time t, and the update, which is the Kalman update. I will not derive this. It's an explicit formula for the ensemble Kalman filter. Given the forecast at time t, how do you take the analysis at time t? And for the particle filter, this is obtained by updating the weights of the system. So essentially, maybe a picture at this stage will help. So let me just go back to this picture. So what we have are basically the ensemble, the Monte Carlo approximation at time t. You get an update in terms of Monte Carlo approximation. This is used using either ensemble Kalman filter update or a weight update for the particle filter. And then you use the prediction, use the model to do a prediction of these ensemble members. So that's a two-step process again, and this recursive process continues. Okay, so that's typically what is done in practice. And what we want to study is the stability of these kind of algorithms. So let me introduce the notion of stability of these algorithms, firstly in terms of a picture. So at time 0, let's say, we start with two different distributions because we don't know exactly what distribution to choose at time t equal to 0. The initial condition is unknown, and we choose some arbitrary distribution. And let's say we choose two different distributions shown like a starfish and a flower, and we want to see what happens to this iterative process as we go forward in time. So we'll start with one of these distributions, go forward in time, apply this predict, update step, and at some time m, we will have the posterior at time m, and the process will just continue. The stability of the filtering theory problem essentially is identical to the usual definition of stability, which is you have two different initial conditions. As you go forward in time, do those initial conditions converge towards each other? And as n goes to infinity, do you get the same or similar distribution function? Or do they diverge away from each other? So I haven't shown the divergent or the unstable behavior in this picture, but the definition of stability is exactly the same. Start with two initial conditions, and if those two initial conditions lead asymptotically in time to similar or identical behavior, then the system, this filter is called stable. Otherwise, the filter is called unstable. And so essentially you can think of this as the algorithm, filtering algorithm, that forgets the initial condition and eventually gives the same answer. Yeah.
Can I ask if this
Yes,
is a property of the dynamical system or a property of the algorithm that we use to estimate?
So both, in the sense that what we want to understand is whether the filter is stable. And a filter being stable can be affected either by the dynamical system itself being stable or unstable, or something else being the observations. And so both of these matter in this case. And maybe the other way to state it is that even though the system may be stable, your algorithm may not be stable, and vice versa. That's possible. And we'll maybe see some examples of that later. Yeah. Actually, now that I say it, I don't think I have examples of unstable filter in this talk. I can describe them in words to you later if needed. I'll show examples of stable filters. Okay, so the mathematical definition is essentially what you would expect. So remember, I said that pi is the filter. Now we need to, so there's a bit of a inflation of the notation. So pi is the filtering distribution at time t, so pi t. But now we want to explicitly put in the initial condition. So let's say the initial condition mu, which was one of these initial conditions here on the top, or nu, another initial condition at the bottom, those will have to be indicated in the filter. So pi mu t is the filter with initial condition mu, and pi nu t is the filter with initial condition nu. And I want to see whether as t goes to infinity, asymptotically in time, they converge towards each other. Well, but now we are talking of convergence of probability distributions. So then this is a slightly more evolved. So you can't just say whether they go towards each other, but rather you want to say whether it is in distribution or in expectation and so on. So this is a weak definition of filter stability. That does this hold true for all, let's say, bounded? Actually, this should have been bounded continuous functions. But so that's one notion. The The other possible notion is that if you look at the distance between these probability distributions, and these could be some appropriately chosen distance, does the distance between the two distributions go to 0? So this comes much closer to the typical definition of stability, where you say that two initial conditions, the distance between two initial conditions converges to 0 or not. But of course, now this is on the space of probability distributions, so a bit more complicated. Yeah. Okay, so this is basically what we would like to study. Right? So for the linear dynamical systems, again, this was the continuous term formulation. I will skip the results that were obtained in this paper, which was a kind of extension of the results much earlier obtained by Ocon and Pardo and so on, but for deterministic systems. The reason for why the deterministic system results are much more mathematically very different is because if you think of them, the deterministic systems at singular limits of stochastic dynamics, then it's not so straightforward to extend the results for the stochastic systems in this case. So I will skip describing the results precisely right now. Okay, since let me not talk about this. There were a couple of different results. One had to do with consistency, and the other has to do with filter stability, and both are related to each other for deterministic systems, which is what we use in proving those results. Okay, so without stating this, just a brief review of what was known earlier. Some of the earlier work has been summarized in these review papers. This is kind of not a very exhaustive list, but fairly representative of what are the known results. And most of these do cover almost everything that was known about filtering theory stability up to the time that they were written. Yeah. Some key assumptions that go into these results that are not valid for deterministic system have to do with ergodicity of the system. That's not the case for purely deterministic chaotic systems. There is a very strong mixing kind of property that is used that's not available for these. And in the linear setting, and again, the generalization for nonlinear setting, controllability of the signal is also not available for deterministic dynamics. So because of these lacunae, the mathematical framework that is developed for proving stability of deterministic system needs to be quite different from what is available in these previous works. So that's roughly the summary of the mathematical difficulties in words. Okay, what we are interested in is if we have a numerical algorithm, then how do you study stability? So let me maybe state this in a picture in a minute. Right? So essentially, it's an extension of the picture which I had shown earlier. So think of this attractor which is shown in these green dots in the background. Right? If you start with 3 different initial conditions which are shown in blue, so this initial condition on here, another initial condition which is shown here, and another initial condition which is shown over here, 3 different initial conditions of the filter, quite distinct, very, very different initial conditions. As you go through the filtering process, do this ensemble that you see become more and more like each other. So the blue dots are at the initial times, something like time 0 to time 20 for a specific dynamical system, which I will describe in a minute. So 0 to 20 is the initial 20 time steps. The next 20 to 40 time steps are indicated in magenta. So these colors over here, whereas the much later time steps, 40 all the way to 200, are indicated by these kind of greenish dots all the way scattered across this. So you can see that the blue dots start off at time t equal to 0 at very, very different initial conditions. So these were three specific choices of initial distributions with different means, and this is the one, this is another one, and this is the third one. But even starting with these, the point of these pictures is that the later distributions shown by magenta and much later by these greenish ones start to look almost the same. So for example, these ones, which are at time 100 and 200 and so on, are almost the same across the three different figures. So these filters kind of come towards each other as time progresses, even though at time t equal to 0, they are very, very different. And we want to capture this numerically and make it more quantitatively precise. That's essentially what the aim is here. Yeah. So what are the tools that we use? The tools that we use are as follows. What we want to capture is some distance, and in this case, what we capture is a distance that is Wasserstein distance. So I will not describe what exactly is a Wasserstein distance. It's basically a distance on the space of probability distributions that can be computed numerically by using an algorithm that is called a synchron algorithm. So the synchron algorithm allows us to capture distances between probability distributions where the computation of these kind of distances was a extremely challenging computation problem until maybe 10, 15 years ago, actually even less than that. And the synchron algorithm that was developed over the last maybe 10 years or so has made computationally it is feasible to compute these distances. So I will not go through the mathematical definition of this synchron divergence, which is what is computed by the synchron algorithm, which is then approximation of this Wasserstein distance that is defined over here. Yeah. So just the summary of this is that the synchron divergence only recently has given computational tools to compute these distances, which is what we will use later. Yeah. Okay. So this synchron and now, sorry, there is a bit of a overload of the notation. As I mentioned, there is a filter pi, which depends on the initial distribution mu. The filter, of course, is at some time step n. So pi n, or what I indicated, pi t. So pi, the filter at time t, which is dependent on the initial condition mu. But in addition, since we have a numerical filter, for that we have the type of the filter that is we are using and the number of particles that are used for the Monte Carlo approximation. So it's a bit of a mouthful. You have to deal with dependence of this numerical filter on each one of these objects. What type of filter you are using? Ensemble Kalman filter or the particle filter? What is the size of the ensemble, the Monte Carlo approximation that we use? Do we have a particle filter with number of sample, with the sample size being equal to 20 or 80 or 100 or 5,000 and so on and so forth? The initial distribution that we choose and the time, and we want to let t go to infinity or n goes to infinity limit of this is what we want to study. Yeah. So all this bunch of different aspects that we study and try to show that some of the results that are commonly used in some of the filters that are commonly used in practice are in fact stable for some of the systems of interest. So we show this numerically, for example, for Lorenz system, which is quite commonly used. There's also a bit less commonly known system, which is called Lorenz-96. This was a system introduced by Lorenz in 1996 to study an n-dimensional chaotic dynamical system with just one single parameter, f. It's quite a remarkable system. Sorry, I should have put down the equations of this in here. I didn't include it. So Lorenz-96 system we study for 10 dimensions, 40 dimensions, and currently we are looking at much high dimensional realizations of this system as well. And as I said, we start with three different initial conditions, initial distributions, which are either different bias or different precision. And using these three initial conditions, we want to study the filter. Yeah. And here was the pictorial description which I already talked about. So let me skip that. And using this synchron algorithm, we can actually compute the distance between the filters at assimilation step n. And what is basically shown here is for a whole variety of different initial conditions and for a whole variety of different filters. In this case, the particle filter with different size, with different ensemble size, either 250 particles or 500 particles, 1000 or 2000 and so on. We plot the distance as a function of time. And as you can see, the distance, even if it starts being high, as a function of time, it very quickly reduces to a very small value. And this very small value is not numerically 0 because of the lacunae or because of the limitations of the synchron divergence. But they do stabilize to some constant value. This value is indicative of the 0 of the Wasserstein distance. And we study in detail about exactly how this 0 is affected by the sample size, by the kind of specific algorithm that we choose to compute the distance and so on. So that is something I'm not going to discuss in great detail here. But think of this as a numerical 0 for the filter. So the numerical 0 for the Wasserstein distance is roughly the value 2 or 2.5 and so on. So that's the illustration of the distance between the two filters dropping down to 0 very, very, very quickly. And in fact, it turns out that this drop is okay. So this is just the summary of what I said in earlier, that the particle filter quickly forgets the initial distribution. In fact, it is stable numerically, can be seen to be stable, and for a whole variety of different setups, this is really true. Okay. The same applies for ensemble Kalman filter, and I'm not going to describe in detail. We can actually do the comparison between the ensemble Kalman filter and a particle filter. It turns out that a particle filter is much more stable in the sense that the distance drops to 0 much quicker in the case of particle filter than in the case of ensemble Kalman filter. We are still trying to understand the reason for this between the two different filters. And I'll not read out the full summary in this case. It is just a summary of what I just said earlier. We can also look at the distance between the ensemble Kalman filter and the particle filter. So just to quickly mention, remember what I said earlier, numerically, the distance doesn't quite drop to 0, but it drops to a smallish value. In this case, the smallish value happens to be less than 2, maybe 1.5 or so on and so forth. Whereas, if you look at the distance between the particle filter and ensemble Kalman filter, that actually does not drop to 0. It remains a small but finite distance. And so the picture is that the particle filter by itself is stable, the ensemble Kalman filter by itself is stable. But when you look at the distance between the particle filter and ensemble Kalman filter, they are not they don't converge towards each other. So there is a distinction between these distributions, even as time t goes to infinity. In this case, infinity is 300 or 400 and so on. And we are still trying to understand why that happens and the implications of it in practice and so on. Okay, so I'll skip this part for now. More details of this. And we can study quantitatively what is the relation between these various distances. And I will skip this for lack of time because I'm almost out of time. So don't forget about the relation between stability and accuracy, which now we have some handle on how to study using these synchron divergences. Okay, so just a quick summary. What I talked about is the stability of these filters, in particular the notion of stability, what exactly do you mean by stability? And the main difficulty is that if the system is not controllable, as is the case for deterministic systems, then mathematically proving the stability becomes difficult. But in fact, we also looked at examples such that the assumptions are satisfied, and the numerical study of stability indicates that many of the commonly used practical algorithms are stable. A better understanding of these filtering distributions is something that we need to get into. The theoretical investigations of the relation between consistency and accuracy or stability, the parts which are skipped towards the very end, and understanding the small noise limit, which is a mathematical problem, which is a very difficult mathematical problem, but implications of these small noise limits for the practical applications is something that we'd like to take up. So with that and these references, I'll stop here. Thanks a lot.
Thank you, Apte. So the forum is open for questions, clarifications, doubts.
Amit,
Yes.
once again, a very naive question.
Yeah.
Although I understand your point is different. You focus on filtering and the distance. Now, but my point is, how you get the initial distribution from the real data set or maybe model set?
Yeah, so in fact, the whole reason for studying the stability problem and being sure that the filters are stable is that the initial distributions are not known and they are in some sense arbitrary. And just like for dynamical systems, you'd like to kind of say that, okay, if you don't know the initial condition, then how do you study the dynamical system? And then you need to know something about the stability properties. It's the same here. We do not know the initial distribution. So the prior at time t equal to 0, whatever t equal to 0 is for your problem. If we don't know the prior, but if the filter is stable, and that can be shown a priori, say, then lacking the knowledge of the initial distribution is not a handicap. Because if the filter is stable, you start with the arbitrary initial condition and it will converge towards the actual filter over time.
But anyway, but for a given a dynamical system, you know the basin.
Yes.
So you can have an idea of arbitrary initial conditions. What does it mean by arbitrary initial conditions?
Yes.
Right.
Okay. Yeah, that's true.
For a real observations, so you do not have a model to start with, just a data set.
Yeah.
So where you get the distribution at time t?
No. So a distribution at time t should be sufficiently general that it captures, so to say, the broad behavior of the system. I mean, it has to involve some knowledge of the system. Let's say, for example, if you think of the Earth system, right? You can't take a completely arbitrary initial distribution, but then the initial distribution, for example, can be obtained by some long simulations of the system in the past.
A long observation data.
Model. Yeah, okay. Partly or possibly observational data or just a model simulation. So if you run your model for sufficiently long time and just take the statistic of that or distribution coming out of such a long distribution simulation, then that can be obtained, that can be used as the initial prior distribution. Because that will automatically involve some of the constraints that you want to put in. For example, the temperature in Pune is between, let's say, the minimum is never, it's say between 0 and 30 degrees Celsius or 50 degrees Celsius.
So let us say if you know that a week in the March, let us say February, a particular week, we know the long data. So we get a distribution from that 100 years or something like that.
So that you can take, but the main problem is that the observational data sets are extremely sparse.
Yeah.
So you don't really have enough observations for all the different variables of interest.
Yes.
And that has to somehow come from the model itself. That simply cannot come from observational data sets.
Yeah, of course.
They're too sparse. So
observations are univariate. Yes.
Yeah.
It's a multivariate.
They are very sparse and it's not possible really to obtain those initial distributions purely based on observations.
Yeah. Thank you.
Yeah.
Yeah, you can go ahead. Yeah.
Yeah. Hi, Professor Apte. Very nice talk. Thank you.
Yeah, thanks.
I guess so. You showed this notion of stability that if any distribution you start from, you would eventually converge to the same distribution.
Yeah.
So, like in typically in this Bayesian framework, so people prove consistency. They say, well, as you get more and more observations, you are going to do that. You're going to converge to the right state.
Yeah.
So here, is there such a notion? And the other question was, well, is like, so you mentioned some theoretical developments, like trying to prove this kind of notion of stability. And so I think can you go over that again, please?
Maybe going over the details is a bit will be a bit difficult to do right now. But just to mention about consistency, at least for the deterministic systems, under the assumption that are not stated here explicitly, which have to do with the chaotic, which have to do with both the what is called observability, that is, you need to have sufficient observations in order to be informative. That's one aspect. And the other is something to do with how the actual system behaves in time. And under those assumptions, which I'm not stating mathematically here, we do prove something about consistency of this of this system. So that is the distribution at time t equal to 0, which you asked about earlier, is in fact consistent in the sense that it concentrates towards a true initial condition.
Okay.
And under the assumptions that are in this paper, we show the consistency result. And in a way, our proof goes via the consistency result. And so on. So, yeah.
And so is the idea
but there is no consistency really for the state at time t, because the state at time t will have uncertainty which does not go to 0. That's partly the result of the chaotic nature of the system.
Okay. Thank you. And so is the idea that even if you are not consistent, you can still do predictions well? Is that?
Not so there is an inherent uncertainty limit beyond which you cannot make more precise predictions at all. That is the so even though, for example, the initial condition had some notion of consistency associated to it, the filter itself at time t does not enjoy that at all. So there is a inherent uncertainty in the filter, which you cannot avoid. The filter is not consistent in the usual way. That is, as observational noise goes to actually, I'm sorry, at least not provably so. I'm not sure if it is or not, but you can't prove. At least we can't prove it yet. And I really doubt whether that will actually be the case. It's highly unlikely. For these chaotic systems, it's highly unlikely that the filter will actually concentrate towards a delta distribution.
Yeah, but no, I guess you had these examples where you're using two different filters, the Kalman filter and the and the other filter, and you showed that the distance between them is not going to 0.
Yes.
Empirically.
Yeah.
So does that mean that there isn't a truth that the filter should do?
No, but those are two different numerical filters. And none of them necessarily capture the true filter.
Okay.
So it's not clear that there is so the relation between the true filter and this numerical filter is a complex question in and of itself. So.
Okay, thank you.
Yeah.
Okay, Amit, I think the students has to go to the next lecture.
Of course, yes, I can imagine.
Okay, thank you. Maybe I will ask them to write to you if they have
Sure, of course, that will be fine. Yeah.
So I would like to conclude the session by thanking Dr. Professor Amit for accepting our invitation and giving a very wonderful talk. Thank you. Thank you.
Yeah. Thanks a lot. Yeah.
I will write to you the other details by email.
Sure. I think that sounds good. Yeah. Thanks. Thank you.